Welcome to the beginning class in Grasshopper. This would be considered week 1 of Grasshopper in computational design bachelor degree for the 1150 class. This particular video is replicating the tutorial that was run on the 14th of March 2018, and it effectively assumes almost zero knowledge in Grasshopper prior to using it. What you will need is Rhino installed. If you have Rhino 6 installed, that comes with Grasshopper already installed as a plugin. If you have a previous version of Rhino, such as Rhino 5, then you may have to go download Grasshopper from grasshopper3d.com and install that before it works. Once you've opened Rhino, all you need to do is type Grasshopper into the command line and hit enter, or there's a little button here to launch Grasshopper if you're using Rhino 6. And this is a predefined script that we're going to be running through, which was written by Christina Ramos, who is a course convener at UNSW in Australia. So the purpose of this particular tutorial is to create some hyperbolic paraboloids, which are these funky twisted geometries here, and then to rationalize those geometries into triangular segments, which we can see if I were to hide this. So we can see that then rationalized into triangles. And then as well to give this particular surface some thickness so that it is 3D printable. So Christina's set out two particular scripts here, but the script that I ran through in the tutorial is a little bit different. After talking with Christina, she didn't have a problem with that. So I'm going to try and keep to that particular script layout as much as possible. Just a note about some of the things that you might be seeing that you wouldn't see if you were just starting from a raw install of Grasshopper is I have various plugins installed. So you can see here Wobbegong and Kangaroo. Actually, Kangaroo is a bad example if you're using Grasshopper 1. So Squid or Wobbegong. So these are plugins that are installed and they just add some extra functionality to Grasshopper. And a really cool one for education purposes is bifocals. What that does is it gives every component a name above it as we place them. If I were to have this off, so I'll just turn this off for you. Is it going to turn off? If I delete it, it will go. No, okay. Let's try that. Okay, yeah. So when it's not there, these little battery component type things won't have names. So I use bifocals just so that it's easier for people to read and work out what's going on. Plus, I like to have Grasshopper set up so that the icons are shown on the components. A lot of not by default, Grasshopper will have your components set to display text, so that, for example, a line component will be displayed as LN. I personally prefer to teach with icons, but in case someone is unaware of what a particular icon means, then we've got the text above that. Another thing, just for beginners, just to note, I have another setting on, which is to draw obscure components. You can get that under View, Obscure Components. So with that turned on, your Grasshopper ribbon will fill out to maximize the width of your screen. If you have that off, you can see, by default it will be off. It will only fill to a very tight zone and you'll have to click into the drop-down menus to get things that aren't shown in this sort of compact view. So if you've got a big screen, and most professional Grasshopper users will be using Grasshopper on 2 screens, not 1, then it's good to have obscure components turned on, and it's also a really good way for beginners to go through and actually find out what Grasshopper is capable of, because there's no way that any video tutorial is going to or degree is going to explain every single component, and so it's really good to actually go through and explore, and the icons have been made quite well to explain what the particular components do. Specifically as well, if you don't know what you're looking for, or if you've got an idea of what you want but you don't know if it exists, the tabs in the top here, they go all the way to display. Anything that you see here beyond display is a plugin that I've installed. So from parameters, maths, set, vector, curve, surface, mesh, intersect, and transform and display, that basically categorizes all the raw or vanilla Grasshopper components. So if you were to be wanting to work on something that involved, or if you wanted to run a component that, let's say, added 2 numbers together, that's probably a maths component. So we go into tabs, and we can almost immediately see under operators there's the addition, but we could also write a script that adds 2 numbers together. And so here's some C# or Python, or we could write a little maths expression. Another example of that would be if I wanted to create a curve or a spline, then that's a curve. So I can find that under the curve tab, and here we go. Here's spline, and then here's all the various different ways that we can create splines. So there's Grasshopper's laid out in a way so that if you aren't aware of something existing, or you might not know its name, then it's actually quite simple to go find that. Plus, it's a really good way of exploring. So one day, if you don't necessarily have a deadline or something important, and you just want to have a bit of a muck around, it's worth actually going through some of these tabs and actually working out, this is another plugin, working out exactly what some of these things do. So like, what does octree do? Even though I'm highly unlikely to explain what this does in the beginner class, this is useful, and it's worth playing around with it and seeing what it can do. So everything's there, everything's in front of you, so there's no excuse to not go exploring. Okay, so if we jump into actually writing this script, if we just go back to looking at this geometry again, in class I ran through a really basic, well, not basic, but on the whiteboard I had a pseudocode of this. A pseudocode is effectively like a diagram of code. It's something that a lot of coders might do unconsciously in their head before they actually go about scripting, and it's a good exercise for beginners to learn maybe some of the steps that's required to create this. So actually using this outcome now, what we need to do is create some steps that we might take manually to draw this, and then we're going to replicate them with the Grasshopper code. So those steps are, what we need to do is define a circle, so we can see the points on the outside of this shape actually on a circle that we can't see. So if I were to just go into Rhino, and draw a circle, we can see that those points sit, the edge points sit on a circle, and there's various ways of drawing a circle. I just drew a circle with 3 points, but I think what we might want to do is define a center point for our circle, and then we can define a circle from a center point and then a radius. So in this case, it looks like the radius is 18, but this will be a variable in our script. So there's a second circle, and this time I'm going to draw it from that point, and that defines the inner set out for these kite-shaped diamonds. And the process involved is actually then taking a circle and dividing it into points. So for example, if I were to say, I can actually see 1, 2, 3, 4, 5, 6. So what we're doing is dividing the outside circle by 6. So we get 6 points on the outside, and we're also dividing the inner circle by 6, but it's offset by half the division of the segment. And we'll sort of talk about some clever ways of dealing with that as we work through the script. And then what we're doing is drawing a line between, or a shape between these particular points, and we're doing that as an automated list. And so we do that 6 times, and we're kind of avoiding the fact that this is 3D at the moment. But then instead of drawing a curve or a line, polyline, we're actually drawing a 4-point surface. So if I just use Rhino to do that, then here's a 4-point surface, and if we were to then control that surface in 3D, we're effectively moving 2 points vertically, and you can't have, like if you have a 4-sided shape that isn't planar, then you can resolve the geometry of that shape by making it a hyperbolic paraboloid, which is what we're looking at here. And that's what Rhino and Grasshopper will automatically do if you start to move those points out of the original plane. So then to rationalize this, I'll just turn that on instead. There's a line that's effectively worked out, it's cut through this hyperbolic paraboloid, and I could probably we'll avoid doing that in Rhino just to avoid taking a whole bunch of steps. But it effectively assumes that there's a point that exists on that line, and actually I'll put a point on the surface just you might as well. Let's just do a projection up. So now I'm not taking any precautions in making this accurate because it's kind of just a sketch, but there's effectively a line that goes from this corner of the shape to this corner, and on that line we're finding a point. So if I throw near on to snap, so we're finding a point on that line. Now if I delete that, we can see that point there, and I could even snap it maybe closer to what the script is currently doing. And then we're just drawing triangles between these points and then that middle point, and that's producing the rationalized version of the hyperbolic paraboloids. Okay, so there's a logical step-by-step process that we would have to do this to make it manually, and all I would have to do once I've made one of these things is rotate it 6 times, but the script effect is going to give us far more power and control over the outcome of this, and we can create many variations of that. So it's far better to make a script. And so what we will do is start that script from scratch. So I'm going to hide the components now in Grasshopper, and so we're going to start with that initial step, which was making a circle. And I'll just snap this so that it's a bit easier to organize. So we've got bifocals. Okay, we're ready to go. So if you remember from the very first step, to make a circle, there's a few ways, and in this case we're going to just use maybe the most basic way, which is to define a center point and a radius. And in class I asked if people wanted to define that using a Grasshopper defined point for the center, or a Rhino defined point. So just to sort of gloss over those two options. By the way, just to actually get a circle, you can grab them from the curve tab under primitives, and it's this particular CNR circle that we want to use. And it has 2 defaults. There's a default in N for the normal, and we can sort of avoid talking about that at the moment. And it has a default value of 1 for the radius. And so we just needed to find a center for it. So we can do that by going to vector, grabbing a construct point, which I'll just leave the little arrows up there for a moment. So what this does is takes 3 numbers and it defines a point in Cartesian space. And you can see by default, there's like a little green cross here at the origin. And if I deselect that, that's red. And so if I were to just plug that in immediately into the circle, we'll get a circle defined at that point and we can see the default 1 radius. So that is like almost the most simplest Grasshopper script you'll ever see. We want to make these points movable, so we need to be able to put numbers in these, and one of probably the most common component you may see in a lot of scripts is a number slider. So the number slider, which can be found under parameter and in the inputs section, it's this little arrow over a bar. So number sliders, effectively, if I copy paste that, so I'm hitting Control C and then Control V, they allow us to put variables into our inputs, and then we can grab the handles of that. I'm just going to leave Z at 0 actually for now, and we can grab the handles of the slider and effectively change the script based on these new variables. So now this point's now at 1, 1. If you want to edit a slider, you will need to double click the dark gray section of it, and that will bring up the slider edit dialog, and we can change the slider's value rules. So we can define whether or not it's a floating point number, which means that it'll have decimal points after it, and so and you'll it allows for smooth transition as you move the mouse up and down. The integer option, which then says that the value can only be a whole number. So in this case, if you're going from a number 0 to 1, then there's only really 2 options. Then there's even numbers and odd. So with these particular rules, you can then also set the number of digits that come after the decimal point. You can set the minimum value, the maximum value. So in this case, if I set this from 0 to 10, the range will change immediately to match the distance between the two. And if you change the range, it'll take the minimum number and then change the maximum number to meet the range. So in this case, if I set, I'll actually cancel that, set this to 5. And then if I set this to 20, then we'll see the max range move to 25. There we go. And so we've now got a slider that has limited itself at 5, and we can slide that all the way through to 25. Cool. So there's a few little shortcuts that you can use to generate sliders, and we'll use them to control the radius of the circle soon. But before we do that, the other way of getting a point in just quickly is by grabbing a point that's actually drawn in Rhino. So in Rhino, I'll grab this point, place it in the model, and to get geometry in and out of Grasshopper from Rhino, we use parameters. So here we can grab the point parameter. It's the very first component of all of Grasshopper. And you can find it under the parameter tab. So that'll be orange, so that's telling you that it's empty. And so to fill it with a point, we right click it, we set one point. That'll then allow you to go select which point you want. So we'll pick the one that I just made. And so that we can see that's now being read as Grasshopper geometry because it's a cross. And if we plug that into our circle, we will move the circle to our Rhino point. Now this Rhino point's still in Rhino, so it's selectable and we can move it. But you can see I can't select this Grasshopper geometry that's set out by the slider. So there's a relationship here now between Rhino and Grasshopper. And I'm going to use this point now instead of the construct point. Sorry, I don't want to move that one. So we use this point now instead of the construct. So we've got and I'll just get rid of that actually. So we've got a point, we've got a circle, and we want to be able to control its radius because having a radius 1 circle and only a radius 1 circle is rather boring. So instead of getting a slider the way that I did before, there's a few shortcuts, and that's by double clicking. And you can grab other components if you know their name off the top of your head. But if you type any number, so for example, if I typed 5, and I keep forgetting this, and hit enter, then it'll generate a slider for you with that number, and it'll set the minimum to 0 and the maximum number to the nearest unit of 10, not unit of 10, sorry, factor of 10. So in this case, the highest 10 factor above 5 is 10. If I double clicked and wrote 55, then the highest number above that will be 100. So it'll go from 100 to 1,000 to a 10,000 to a 100,000, a million, etc., etc. Just note here that because I typed 5 and 55, that it automatically will make these things integers. If you want it to have a decimal point, you will need to add those, and the more decimal points you add, the more accurate that float number will end up being. So the default with these sliders is 3 decimal points, so you will need to add 3 decimal points if you want that to be by default with the double click. Now mind you, these are all editable once they're placed, so you don't necessarily have to put up with whatever shortcut that you may have accidentally put in. And then the final little shortcut is if you were to say, let's say 8.24 is greater than 87.54, that will then create a number slider with those two minimums and the minimum and maximum. So it's just a quick way of actually controlling almost every variable you have there. So a lot of information on how to make sliders, and I'll probably stick to the one. We'll stick to the one that goes to 10 for the radius. Actually, we might make it go to 30, and we also probably want it to be a float. just because we want it to have a nice fluid relationship as we slide it up and down, like so. And so this is now defining the circle, one of the circles that we drew in the pseudocode. And so what we'll do is we'll assume that this one will be the larger circle. Yeah. No, we'll make this the smaller circle. So we'll just set that to 10. And just as a note, I'm double clicking the inside of the variable slider zone, and I can type the number that I want. And what we're going to do is copy and paste this component. So I'm just hitting Control C and Control V there, and that's then we can change the variable to make that a larger circle. And just note, because I only selected these two components and not the point, and when I copied and pasted, it maintained the connection, and it's effectively sharing this point now between the two components. So if I move the point, both the circles are going to move. So that there's a relationship now where the point is a parent and the circles are child elements of that. And so this is effectively why we can start doing some really clever things by sharing parameters and setting relationships up between geometries. So the next step from there was we needed to divide our circles. So we're going to divide them so that then creates that kite shape. So I'll just quickly throw in a kite that I think this might want to make, like so. And so to do so, we can find divide curve under curve division. And what that will do is divide your curve into equal segments. So if I plug both our curves into two separate divide curves, we can now see points. These curves are getting divided into points. And just we'll give this a bit of a rotate. Set my snaps correctly. Maybe get a mouse pad. There we go, this is better. So what we're looking at is we wanted a diamond that effectively went from the center point to our outer point, and then it was going in between sort of halfway on either side. And so this is where we can actually start creating some clever relationships between the data so that we can get that midpoint in a efficiently coded way. So one way would be to rotate all these points, but there's a way that effectively teaches a concept really well, so we're going to use that. And that is if we were to generate double the amount of points. So for example, if I were to generate 20 points, actually let's use a slider for that, 20. If I were to generate 20 points instead of 10, then what we effectively have to do is, if we consider the points in each circle as a list, where and I can actually use Grasshopper to help me explain this particular concept. That might be a bit too big. So if we consider each point a list, then what we need to do is we need to connect our diamond with every even point. So if I draw a second diamond now, we are going to skip the odd points, and we're only going to use the even points on the outside, but then we want to skip the even points on the inner curve and only use the odd points. So a way to isolate the points that we want to use is by using a Boolean pattern system. A Boolean. So if we've learned about different types of variables today, we've learned about float numbers really quickly. So numbers that have a decimal point. We've learned about integers, and another non-geometric variable is a Boolean. Booleans are effectively things that can only be true or false. So what we can do is say, define a pattern that says a list is there. Sorry, let me just gather my thoughts. We can define a pattern that we can run over a list, and that pattern will effectively split that list into two lists, one list being all the odd numbers and one being all the even. And we'll say the first one is even, and then the second will be odd. So the evens we could assume might be true, they satisfy a true condition, and then the odds satisfy a false condition. So the component that will do that for us is dispatch. We can find that under set. So just to explain what set is, it basically is all the Grasshopper functions that apply to lists, and we'll go into lists a bit later. Not in this particular video. We're using lists, but we'll explain what lists do in more detail in future tutorials and hopefully videos, because I'll be recording those tutorials. So our dispatch takes a pattern, and that pattern has to be true or false. Grasshopper and computer science defines true or false as either 0 or 1, where 0 equals false and 1 equals true. So if I were to create a pattern like this, 0 and 1, and I set that, so I just completely skipped over something that I subconsciously use, and that is the panel. So panels, we can find them under parameter and input. The funny thing about panels are that they're not just inputs. So you can use a panel to view what is in a wire, and so these are wires that we're looking at. Yet again, another thing that I've conveniently skipped over. So you can view what's in a wire. I'll explain wires a little bit later when we use them and do a bit of a funky wire gymnastics with them. So we can see what's in a wire, and in this case we're looking at points. So we can see that these points, that they have an X, Y, and Z coordinate, but then we can also use panels to create data that then goes into panels. Inputs. But if we need them to be understood as a list, in this case this isn't being understood as a list. It will only be understood as a list if you sort of see this alternating tinted pattern and with indexes. So this list, to make this a list, we need to right click it and then turn off multi-line data, and then that will display that as a list. So if I then plug that into our dispatch, and I just turn off our point lists, if I plug my divide curve now into the dispatch, and we preview the elements coming out of A, what we're actually it might be good to still have that display number on. So what we're looking at is 1 is going to send elements to A, or true is going to send elements to A, and 0 or false is going to send elements to B. And if we highlight over that, we can see here dispatch target for true values, and for B, dispatch target for false values, so 0 or false. And so just quickly set that back to 1 just so that's a bit bigger. we can see if I select the A's, they're going to be the second value in the list. So if a list, we can see here, lists always start at index 0. So 0 is an even number. So 0 is going to be applied to 0, or false is going to be applied to 0. So 0 is going to end up going to B, and then true, or 1, is then applied to 1. So 1 will end up going to A, then 0 will be applied to 2, and then 1 will be applied, true will be applied to 3. So what we're actually looking at is a pattern of even, odd, even, odd, even, odd, even, odd. So 0 or B is going to be our even numbers, and 1 or A is going to be our odd numbers. So we can see here, highlighting this in green, we can see A is all our odd numbers. So going from 1, 3, 5, 7, 9. And then if I were to plug B into that point, now all the green values are 0, 2, 4, 6, and 8. So this is a really useful way of effectively, if I would hide this, and I'll just explain hiding just after I do it. If I now just grab the A values out of this dispatch, we can see that they are the points that we need to define the middle corners of our diamonds. And if I were to utilize this same script with our lower divide curve, so the outer curve, then we want the B or the even values, and they now correspond with the points that we want on the outside. Now, it's very important that we have a system that has an even number of points. So we could either go into our slider and convert that to even, but instead of doing that, what we'll do is we will times our slider by 2. We can do that by going to math, going to script, and expression. I quite like expression because it allows us to write slightly more complicated maths functions versus just multiplying two numbers together. But in this case, we're going to only multiply this value by 2, and it's always going to be 2. So 2 is kind of like a static value. So to do that, what we're going to do is just first define the variables, and the expression always comes in by default with 2. If you zoom in enough, it's going to show you these little black and white buttons. So they effectively give you the opportunity to add and remove variables. And in this case, we're going to get rid of y. And then we'll double click into that, allowing us to edit the expression. And we're going to write x times 2. And for those of you who are familiar with computer-based maths operators, Grasshopper has given you the functions in the top bar. So if you hit the times button, then that'll give you the asterisks. So if you're not familiar with asterisks and times, or for example, / is divide, so instead you can use this division operator, and that'll give you a /. So simple, not simple, but primary school maths functions, and then we've got computer science style functions. So we're going to take our 20, we're going to plug that into x times 2. So the output of this, if we check that in a panel, is going to show us 40 as expected. So now if we plug that in, we're going to get 40 segments, but then when we cull them down into evens and odds, then we're only actually going to see 20 segments. So if I then cut that down to 10, then we get the corresponding 10 segments. So that's us sort of putting a little human logic into this, so that when we write the number 10 in, we get 10 diamonds instead of 5. So that's fortunate. And it also means that this particular number now doesn't have to be even, so we can have this be 11 or 15 or whatever, and it should work. But I'll go back to 10, seeing as it's lining up with my diamonds that are currently drawn in Rhino. Okay, so we've currently got a point that defines the inside. We've got points that define the middle, and we've got points defining the outside. So what we can actually do now is connect these up using the 4-point surface. You can find that under Surface tab in Freeform. What that does is takes 4 point inputs. Our first one is going to be the inside, the center of the circle. And so if we go back to the very beginning of our script and grab the center of our 2 circles and plug that into A, then we wanted to connect to the middle of the middle circle or the inner circle. So that's going to be connected to B, and then we'll connect to the outer circle, which will connect. So that's this one. We'll connect to C. So what we're seeing now is the beginnings of our diamond. But if I just quickly throw in another point parameter, it's empty. So if I plug in this point parameter, it's just going to be the same. It's just effectively organizing it. And then replacing A. And I will not forget to skip over some of the Y functions. I'll explain them very, very, very soon. So we've got 3 points. There's no other really any points in the system other than the ones that we don't want, and we need a 4th point, which is actually, it's there, but if I were to try and connect that up, so that's these guys, the system wouldn't work. It doesn't realize that it needs to go to the next one. So what we need to do is shift this list. But before we do that, I'll explain some of these Y functions, okay? So sometimes you want to, you've made a mistake, so you've put a wire in the wrong place. So you can remove wires by right-clicking them, selecting disconnect, and then selecting point. Or if you've got multiple wires into something, that'll remove the wire. So we can see that's gone back to what it was before. If you plug in a wire into a component, so for example, if I plug this circle in to this curve, then if you then grab another wire and then plug that in, it will overwrite the existing wire. So that by default, if you drag it in, it replaces it. But if you want 2 wires to go into the same input without overriding, then you can hold Shift as you drop it in. And so whilst holding Shift, that then prevents it from overriding, and now we have 2 circles going into this input instead of 1. That'll also mean when you right click to disconnect, there's an option to disconnect all, and instead you can select which one you want to disconnect, and it will highlight that for you. One more little trick is if you have another component that you would rather these wires be plugged into, and let's say you might have 100 plugged in here, so instead you then have to plug your 100 in again. Instead of doing that, you can hold Control Shift, and that will then pull the wires out of the component you select them from, and that will allow you to plug them into the new component. So those are some just sort of wire tricks there. Okay, back to this. We're in the center. We've got the inner circle, but what we need to do is we need this list of points to be understood as 1 point over, so that this will close up this diamond. And without sort of going too in depth into lists, a lot of people would think of lists like what you're seeing here in Grasshopper as a linear list where things go up by 1. So in this case, the starting index will always be 0, and we go to 9. But we can also think of lists as circles. So if I were to plug our points in and size them up a bit more, then yes, I need to talk about hiding things as well. So we can see here that we have a point that is at index 0 and then a point at index 1 and 2. But index 9 could also be understood as index -1. And if we wanted to move index 9 to index 0, so the end to the start, then all we have to do is shift the list by 1. Or if we want to move the start to the end, then we just need to shift the list by -1. No, I'm going to shift the list because we've interrupted this a little bit first. I'll show you how to do the previewing stuff very soon. So under set in list, you'll be able to find shift list. We're going to plug shift the points that we want to shift. And I might actually go and grab the display just so that we can see what this is about to do. So here are the points that we have been moving, that we're going to shift, sorry. I'm just going to make sure that we're shifting them by either -1, 0, or 1. So I'm setting the slider to -1 to 1. We're going to make that integers based value, and so at 0 we're not shifting the list at all. And if I shift the list -1, we're going to see the 0 rotate into the 9 position, and all the corresponding points following suit. And if we go back to 0, if we shift that by 1, we'll see the 0 going to the 1 position and all the following points following suit. Okay, so what that's doing is it means that for our 4-point surface, we can then plug in the 4th point, which is the shifted inner circle, and we want to shift that in the negative direction to create our diamonds. Now, at this point, we need to sort of turn this into 3D because this is very close to becoming hyperbolic paraboloids. So before we talk about that, we'll just talk about how I've been hiding things and showing them. So if we select components that we want to preview or hide, we can hit the middle mouse button or the spacebar. So if I go select these two, hit spacebar, then if we want to preview or show these elements in Rhino, we can select the guy without a blindfold. And if we want to hide them, we can click the guy with a blindfold. So if I just want to show the 4-point surface and maybe the circles, I can select the circles and show them. And there it's pretty simple. So there's a few other little functions in there that I'll show you this particular lesson. But it's spacebar or a middle mouse button away from getting that information, from getting those. And obviously mousing over them is going to tell you what they do. Okay, so we need to make this thing 3D. And to do that, what we need to do is take the outside curve or the outside points effectively and move them vertically. So to do so, we have the transform geometries, transform functions, and under Euclidean, there's a move function. Move effectively takes a geometry and moves it by a vector. So just to really quickly explain what vectors are, they are geometries that define a direction and a magnitude in that particular direction. So if I were to, for example, if I wanted to move this point up 1 millimeter, so I'm working in millimeters, then I would give that vector of z1, so z being vertical, and x and y would be 0. So I'd be ignoring moving it left and right, forward and backwards, and we only want to move it up or down. So in this case, under vector, in the vector tab, vector section, there's unit z. So what that does is it will construct a z vector and it will ignore all the other directions. And if we plug a slider into that and we make that slider, let's say 20 as a maximum, that will move the circle, and as we slide that up and down, in the slider, the circle will move up and down. So now what we're going to do is use one of those techniques that I mentioned earlier with the wires, and that is, instead of using this flat circle, what we can do is we can use the moved circle and divide that instead. So what we're going to do is we'll replace the flat one with the moved one, and there we go. We're starting to get some hyperbolic paraboloids. It's just the middle point needs to also be lifted up. So that's as simple as copying this set of components and plugging our center point into that move, and you can see there it is there, and that just needs to now replace the point that's then going into our 4-point surface. And there you go, we're starting to see some hyperbolic paraboloids that are arrayed. So at this point we can see there, like these two curves there, it lines up with them almost. I'm going to get rid of them because it's at this point that we can actually play with the divisions. So we can go from 2 to 5, and the system, because we've defined a really nice rule set, it will work. It's robust. We can play around with the radiuses, so we can have some really sharp, tight hyperbolic paraboloids, or stretch them out and have them actually utilize their curvature over a long distance. We can play around with the height, and that's not necessarily locked, so the midpoint can move independently from the rest. And we've got a nice little robust script. It's actually it's at this point that you would actually probably want to make this a thin shell concrete structure instead of rationalizing it, because this would actually have a lot more strength in it than the triangular one. But we're rationalizing at the moment because we're just trying to maintain process in the lectures and the tutorials of stepping up from planar geometries to single curvature geometries to double curvature. So what we're currently looking at is double. So now we have to take the steps in making this double curvature planar or rationalized. So the process of doing that is, and just to sort of speed it up, because I believe we're almost at an hour. Okay, so I just want to speed this up because I want to go to bed. So we need to effectively cut geometry through these objects, and in doing so, it'll generate the curve as it cuts through here. So to do so, we need to create geometry that is in infinite and is planar as it cuts through. And so that type of geometry is called a plane. And to generate planes, we just need there's a few ways of generating them, but in this case, we're going to use two vectors. The first vector being the point. It's going to be generated by the center point and the outer point of our geometry. So that way, this plane's, if I visually draw this vector, the first vector line is going to look like so, and then the second vector line is going to be vertical, so it's going to be unit Z again. And it doesn't really matter what value that is. It just needs to be unit Z, or it can't be 0. So we can use vector 2 point. We can find that under vector and vector again, so it's a neighbor of unit Z. And we'll also grab unit Z at the same time. And these two particular components are going to feed into the construct plane component. So this thing takes two vectors, so unit Z and the vector 2 point, and an origin. Our origin is going to be the center point. So I'll plug that in immediately. The center point is going to define the first point of the vector. The outer edges, and just if you tap into your short-term memory, that's these guys. We can preview them just to make sure. So these guys are the outer edges of our geometry. They go into the B section, so that's now creating a vector. Vectors aren't actually visible geometry, otherwise they would be called lines. There are ways of previewing them, but I'm very confident these are doing what we need them to do. So these go into the X parameter of our plane, and then Z goes into the Y, and we can see Grasshopper displays like a little a square with a grid in it. Just note, this is just a display geometry to show what the plane, roughly like where the plane's oriented and where it's located in space. Planes are infinite, so even though it might not be going for infinity in the display, you have to remember that it is going for infinity. So even though it doesn't look like it's slicing through our surface, when we run an intersection on this, so if I go to intersection and I grab, now I'm throwing a new word at you now, B-rep, we find a B-rep and plane intersection, so you can find that there. So what we're going to do is we'll plug our surface into the B-rep input. B-rep stands for boundary representation. It's a really broad term that basically describes 3D surface geometry. So if you have two surfaces that are joined together, or let's say maybe 6 surfaces joined together and they're all square, then I'm likely talking about a cube. Cubes are boundary representations just as much as the surfaces that make them up are boundary representations. It's like sort of saying that something is a curve. So lines, circles, arcs, ellipses, splines, they're all curves. So surfaces are boundary representations. So we're going to find the intersection of that with the plane. And that's going to generate a curve that slices all the way through. And this curve is effectively the element that we're going to find a point on to generate the triangles. So we are then going to grab a point along that, and a really nice way of doing that is with evaluate curve. Because it allows me to introduce quite quickly what reparametrizing is, and I'll explain that very soon. But you can see here, as I've dragged that in, there's a dashed line, a dashed wire, and that's because the B-rep plane intersection component, it generates these things called branches. They're not something that we're going to touch on in this tutorial, but there's something that we will eventually talk about. The quick and easy way to ignore and avoid them for the beginners is by grabbing a flattened tree. I'm not really going to explain what this does, apart from the fact that if we plug our wire in and we grab a wire out, we can see that that wire is no longer dashed. So We're just going to keep away from dashed wires in this particular tutorial. So evaluate curve, it effectively takes a value. If I plug a slider in that goes from 0 to 1, we can see, oh, my bad, I'll just undo that. If I plug that in, we can see that as I slide it up and down, we've got points appearing on our line, but they only go sort of about not even 5%, maybe 5% along the curve. So what that's doing is it's saying at this point here on the curve, that is point parameter equals 1, and if I were to go to 0, then that's parameter equals 0. So 0 is usually always the start of the curve. The cool thing about curves is you can always understand them as percentages. So we can always sort of say that the start is 0% and the end is 100%, or 0 and 1. But to force that to happen, we need to right-click the curve input and select reparameterize. So what that then does is says if I were to put in 0.5, then that's 50%. So that's going to give us the midpoint of our curve. And so that's now the one parameter is no longer here in the sort of like really tight region. Instead, it is at the end. So that's going to give us 100%. So I'll just keep that at 0.5 for now. And so now we just need to somehow get triangles that go sort of, the base of this triangle will go, I'll just try and draw this in Psuedo 3D. So this triangle will go to this point, and then there will have another triangle. So effectively, we just need to use the edges of the hyperbolic paraboloid and have them go to the midpoint. In class, I had everyone sort of reuse the 4-point surface and just sort of re-string points together. But there's a much quicker way of achieving this, and that is by creating pyramids. So all we need to do is get the edges of our hyperbolic paraboloid, and a cheaty way of doing that is if we plug a point surface into a curve component, it'll give us, did I say point surface? If we plug any surface into a curve component, it'll convert, that curve component will convert the surface. So we can see there's the untrimmed surface. We plug that into a curve component, it converts it immediately into the outline curve that defines that surface. So that gives us the perfect inputs required to create a pyramid, or another way of describing that in Grasshopper is extrude point. So this is another surface. We can find that under freeform, and what this does is takes an outline or a surface, in this case we'll just use the outline, and it creates a pyramid to a specified point. So the point that we're going to use is the midpoint along the curve, so that'll plug into the point, and we then get our rationalized surface, our rationalized triangles. So that avoids having to sort of create 4 separate 4-point surfaces, and it creates a nice little robust system. And we can sort of slide our parameter up and down and define where we want our particular triangles to line up. So this is rationalized now. We're not seeing any double curved surfaces. It's all planar. And so now this is ready to be made. We could unflatten it and make it out of paper, but for this particular exercise, we want you guys to learn how to use the 3D printers and use them, and learn how frustrating they can be sometimes. So the 3D printers can't print anything unless they're solid, and this thing is not solid. It's an infinitely thin surface, and just to sort of prove that this is a boundary representation or a big rep, if we plug that into a panel, we can see there's open brep, so it's not closed, it doesn't have a thickness. So what we need to do is, just to avoid any really complicated functions, we've now got there's 5. So we've now got 5 open breps. If we use brep join, which you can find in Surface Utilities, brep join will join any breps in a list together, making them a single brep. And because we've written this in a way that these will always be touching, seeing as it's a radial system, that this will join all of them into a single brep, and that will then allow us to use extrude. Extrude is kind of like move, except it leaves a solid object behind as you move the element. So we're going to plug our brep join into extrude, and we're going to put a unit Z into that. The unit Z is effectively going to define the direction that it's going to extrude and the magnitude of the extrude. So if I'm working in millimeters at the moment, by default this is 1. So just to be safe, we don't want to put anything smaller than maybe like 2 millimeters into the 3D printers that you particular students have access to. Let's go look at my Slack channel. So we want 2, and let's say maximum of 5, just in case, we want to be robust. So 2, we plug that into the unit Z, and we get a much thicker wall. And we're on the home stretch now, because there's only one button. We're 1 button away from getting this back into Rhino. So at the moment, we're looking at dynamic geometry right now. I can select the point in Rhino, I can move it, but I can't select the extruded solid that we've just made. So we need to get this back into Rhino so that we can then export it for the 3D printer. And to do that, we need to bake. So the term is bake, and I guess the really good analogy of that is if we were to bake a cake, we're taking a really dynamic fluid cake mix, and we're putting it in the oven, and it's then baking it, solidifying it, and it's very hard to then take that cake and convert it back into its liquid cake mix form. So the instant we bake, we're effectively detaching the geometry from the dynamic form. Fortunately, we use a computer, so there's always undo and there's always redo. So we want to bake the extrude. I feel like a beginner way of doing that is by hitting spacebar or middle click, and it's this little egg. I really think it should be a cake, but it's an egg. So we use the egg to bake, and then if we minimize or quit out of Grasshopper, don't worry, you won't lose your work if you haven't saved. Then we can see that we have our geometry in Rhino. It's selectable, we can move it. You can see that as we move it, the point that was defining the geometry in Grasshopper isn't moving, so it's completely detached from the dynamic system now, and this is now selectable to be exported to STL format, which is what the 3D printers at UNSW will take. Actually, I think it's probably what any 3D printer will take by default, unless they're really special. So that's it. That's the tutorial from the 14th of March from start to finish. I've managed to cram it into, sorry for the infinity effect, managed to cram it into a 1 hour and 12 minutes. So we converted 3 hours to 1.2. So that's pretty good. Let me know if you have any issues with this. I hope you enjoyed the tutorial. This is the 3rd time I've tried to record this, so here's hoping that it actually did record. If you're hearing this right now, that means it was ultimately successful. And this will, I hope to see you in class soon.